Hello everyone, welcome to my YouTube channel CivilSphere Insights. In this video I am going to discuss an important topic, SFD BMD from strength of materials. This topic is very important. You can expect minimum 2 questions in any civil engineering exams from this topic. This is very important topic and this is very basic things you have to know understand the structure, theory of structure. So this fundamental things you must know it. If you are in civil engineering, you must know it. I will make each and everything clear in this video. I can guarantee that if you just watch this video, your SFD BMD will be strong enough to tackle any kind of questions from SFD BMD. Okay, I can guarantee. And after SFD BMD, after completion of SFD BMD, I will bring some questions, practice questions, 60 or 70 questions. I will bring from SFD BMD. So after watching this video, you will have to watch the practice questions session. Okay. So if you will go through these 2 or 3 videos now, then I can guarantee your SFD BMD will be very much strong. Okay, so let us start with the SFD BMD. So for one thing, I consider that your reaction calculation and support concept is clear. So I'm not giving any detailed view of those things. So I will start from SFD BMD directly. Okay. So what is shear force? So shear force, if I consider this a beam, so if I consider section here, so these are section, right? So this section XS section. So if I consider section, so if I am here, so at this point what will be the shear force? So whatever the shear force available in that section, whatever the shear force available on either side of this section. So if I sum up those shear force, then this is called our shear force. Okay. So this thing is the same thing applies to the bending moment also. So whatever the bending moment is available there in either section, in either side of the section, if I take algebraic sum of those bending moment, then it will be called as a bending moment. Okay. So now we will move to the to understand shear force diagram and bending moment diagram, we have to know the sign convention first. Okay, so let us know the sign convention. So to understand the sign convention, we have to consider a beam. These are beam, and I consider a section here. These are section XX section. Here I want to move from right to left. Right to left. I want to move right to left and I want to calculate shear force. Okay. So now if I here assume this, I am here. Okay, I want to move from right to left. Okay, so at this point how many shear force are there? So consider this as cantilever beam. So at this point how many shear force there? There is no shear force available at this point, right? No shear force is there. So we will consider the shear force. We will assume the shear force as mangoes. Okay, I am just picking up the mangoes. Okay, I will be picking up the mangoes. Okay, okay. So at this point if I standing there, then there is no mangoes available there. Okay, there is no mangoes. So if I be here, this me. Okay, this me. If I be here, so how many mangoes are there? How many mangoes I will be picking up? 5 mangoes, no? So I will be picking these five mangoes. So at this point I have 5 mangoes. At this point still I have 5 mangoes. Okay, at this point 5 mangoes. Okay, at this point I also have 5 mangoes. So what will be the magnitude of those mangoes? So at this point I have 5 mangoes only. Okay, so I have picked up 5 mangoes only. Okay, so what will be the magnitude? What will be the sign of those mangoes? Let us see. There is 2 things. That is our run and loop. Right, upward, negative. Loop means left, upward, positive. In our case we went from right to left. That is our right upward negative. Right upward force negative. and there is no upward force. There is a vertical downward force, right? That is our. So if the force is negative, if the force is downward, then it will be positive, na. So our 5 mangoes will be positive. Why positive? Because right, upward, negative. If the force is upward in this direction, then we would consider it as negative. But here the force is downward, acting downward, so we take it as positive. Remember? Okay, understood? Okay. So at this distance we have 5 mangoes. Whatever the magnitude, positive 5 mangoes. Okay. Now I am here, just right of these 7 mangoes. I am here, still I have 5 mangoes, right? Positive 5 mangoes. And if I am here, how many mangoes I will be picking up? Previously I had 5 mangoes, now 5 mangoes plus, and these 7 mangoes will also added. At that point I am on the dead point, right? So if I am on the dead point, I will be picking up 7 mangoes also, right? So 5 plus 7, and this 7 also plus. Why plus? Because this is vertically downward, but if it will be negative if it is negative, if it is downward, right? But here the force is downward, so our force will be added, our mangoes will be added. But if the force is upward, then we would take it negative. That is our run upward negative, right? Okay, so we have to add the mangoes. So adding the mangoes, we will get 7 mangoes. That is our 12 mangoes. Okay, so here I have 12 mangoes, right? At this point I have 12 mangoes. At the very instant, at this point I also have 12 mangoes, right? So if I am here, how many mangoes will be there? Presently I have 12 mangoes, na, plus 12 mangoes. Okay, so if I am here, so this is our UDL, right? So UDL, how many distance at? So suppose this is 2 meter distance. So we know that calculating total load from UDL, 3 into 2. Okay, this is our load intensity into distance. How many distance it cover? 2 meter. So that is our 3 into 2, 6, right? So this load also vertically downward. If this is upward, then negative. But here it is not a load hour acting downward, so positive. So that is our 6 plus 6. So at this instant I have this much mangoes, 18 mangoes. Okay, got it, everything? So now we will calculate the shear force diagram. We will draw the shear force diagram. So to draw shear force diagram, we need to know one thing. If the load diagram is point load, then we will have rectangular shear force. Okay, if the load diagram is UDL, uniformly distributed load, then we will have triangular or linearly varying shear force. Okay, if the load diagram is uniformly varying load, then we will have parabolic shear force. Okay, now what about the bending moment? If the load diagram is shear force, then we will have bending moment as triangle. Okay, if the shear force is triangle, then we will have parabolic, 2 degree parabolic. Okay, if the shear force is parabolic, we will have 3 degree parabolic. Okay, now if there is no shear force, zero shear force, then we will have a rectangle bending moment. Okay, remember. So here I want to draw the shear force diagram. So here all the force is positive, all the mangoes are taken positive, right? So at this point, if when I will be here, there is no shear force, zero shear force, right? So up to this point, no mangoes, but at this instant I have 5 mangoes, right? 5 mangoes. At this point, no mangoes, only the 5 mangoes. So newly mangoes, there is no newly mangoes, so I have 5 mangoes. So here only 5 mangoes. Okay, up to this point I have 5 mangoes. So 5 mangoes, triangle. Why triangle? Point load, right? So here up to this point 5 mangoes, but as I will get this point, So I will have 5 plus 7 mangoes now. At this point I have 5 plus 12 mangoes. So it will be vertical down or right, vertical upward. Why vertical upward? Because it is a point node, right? Suddenly it will upward, right? So it will sum up to 12 mangoes. Okay, so at this point I have only 12 mangoes only. So take this, continue. Why continue these things in this way? Why? Because this point these are point nodes, right? So we have to take rectangle. Okay, so here what happened? There is a UDL. So if for UDL load we have to go triangular, right? So that is our 5 plus 7, that is 12. 12 plus 3 2 into 6, 18. Okay, so this is our 18. Okay, these are 18. Okay, got it. Now we need to calculate the bending moment diagram. How will you calculate the bending moment diagram? So let us understand the shear sign convention of bending moment diagram. So bending moment diagram, there are two nature of bending. There is our these things. These are this is and this is, right? So here top portion is compression, here bottom portion is tension. Topmost fiber is under compression and bottommost fiber is under tension, right? These are tension and these are compression, right? So here topmost fiber is tension, under tension, and bottommost fiber is under compression. Okay, so this is called sagging and this is called hogging. So if I consider this as this is a face, right? This is a face. So this is our happy face, right? This is our happy face, right? But here it is our this is our sad face, right? This is our sad faces. Okay, so this is called our sagging, this is called hogging. Okay, sagging, hogging. Sagging means that since this is a positive attitude, that is our positive, bending moment will be taken as positive. If this beam bends in this way, then we will take it as positive. This is our happy beam, and this is our sad beam, that is called hogging. Hogging means negative attitude. Okay, so for negative attitude we will take it as negative. For positive attitude, that is happy beam, positive. Okay, so I think you can remember this if you just understand these things. This is a very important thing. So let us see the bending moment diagram. How will you draw the bending moment diagram? I will not apply a sign convention here. Yeah, I will apply okay, you can apply sign convention here, but I'm going to do this in a different approach. There is a formula. Formula means I will prove it. So we know that dm by dx, if we derive first derivative of moment is shear force, right? So if I dm by dx, that is our dx, so f dx, right? If I take it shear force, so if I take integration, so this is our integration, right? So if I take two point, that will be m2. The difference of moment from m2 to m1 is equal to the what is this? This is our area, right? Force area, right? Shear force area, right? So if you know the basic maths from integral application of integrals, this is our shear force, right? So area under shear force, there is our area of shear force from 1 to A, right? So we'll be applying this formula. The moment difference between 2 and 1 is equal to the area of shear force between 2 and 1. Okay. I will take some simple example, and you can do it by your own, whatever. So I will just take one example. So here no load, and there will be no moment, because as there is no load. So here no moment. At this point there is a load, but the vertical moment is not there, but the perpendicular distance is not there, because we know that moment is equal to force into perpendicular distance. So there is no perpendicular distance, that is 0. So at this point moment is 0. Okay, moment is 0. But here at this point, up to the very left of this 7 mangoes, how many loads are available there? 5 mangoes, right? So if I calculate from that formula, then these are M1, right? These are M2, right? These are M3. So there will be ABCD, but I just take a 1 2 3. Okay, so M1 minus M2 is equal shear force diagram area of shear force diagram. This is our area, right? So how many what are the ordinates? 5 ordinate, right? 5. Vertical height is 5, right? Here what is the distance here? If I consider 2, so 5 into 2. Okay, this is a rectangle, right? So the area of rectangle is 5 into 2, right? Okay, so M1 is equal to 0 here. So M2 is equal to, we need to find, so 10, right? So M2 is equal to minus 10. Okay, so the minus 10 shear force was a rectangle, so we'll take it as triangle. Okay, bending moment will be triangle. So here, so from here to here, what will be the bending moment? So we will consider this area. So in this way you can calculate the bending moment shear force diagram. Okay, now we will take an example. This is B, this is A, this is 20, this is D, this is A, this is C, here it is 20 Newton, here there is a UDL of 10 Newton. So if I want to calculate the shear force, so at this point there is no shear force. Okay, as you go right to left, then we will have this load, right? These are 2 meter. So 10 into 2, that is our 20. So here this load is acting downward, right? So right upward negative, but the load is acting downward, so it will be positive. Okay, so this 20 Newton, this 20 Newton, this 20 Newton will be positive, taken as positive. How much positive? 20 into positive. I will have 10 mangoes. Okay, at this point if I here, then I will have 10 mangoes, right? So 10 mangoes positive, na? 10 mangoes positive, but there is a UDL, right? So for UDL we will take the shear force diagram triangular, that is our 20. Okay, 20. Now at this instant suddenly I will have 20 mangoes also. So previously I had 20 mangoes plus 20 mangoes, I have 40 mangoes, but here this is our point load, so it will be vertically up. So here again 20 mangoes, that is if I sum up, then I will have 40 mangoes. These are 40 mangoes, right? So here in this case, if I be here, no newly mangoes picked up except the previous mangoes, that is our 40 mangoes. So I have only 40 mangoes only. Okay, no newly mango picked up, right? That is our 40. So here load is vertical, right? That is our 40 mangoes. Okay, at this point 40 mangoes only. Okay, now here, now there is a mangoes which are placed at an intensity. So how much intensity there? 20 intensity. What is the distance there? 2 meter. Okay, so here 2 meter into 10 20, that is our 40 load. So 40 mangoes are there. So previously I had 20 mangoes, 40 mangoes, now 40 mangoes, that is our 80 mangoes. Okay, so I will have 80 mangoes, that is our vertically, so that is our triangle, right? Because it is a UDL. So I had 80 mangoes. At this point I had 80 mangoes. Okay, all things are positive, because right upward negative, but here right downward, so positive. Okay, now I want to calculate the bending moment. So I will just calculate the bending moment. How will calculate the bending moment? Let us take this portion. Okay, so here MB, right? These are MB, right? These are B, this is our C, this is our D, this is our A. Okay, so MB minus MC is equal to area of the shear force. This area half into ordinate 20 into this portion 2 meter. So I will have MB, value of MB 0 minus MC. We want to find that MC. 2 to cancel, then we have 2 20, that is our MC is equal to minus 20. So shear force was rectangular, right? Sorry, shear force was triangular, so we will have parabolic, right? These are parabolic, okay? Parabolic bending moment. So here in this case, now we need to find the MD value, right? So MD minus, not MD, from MC to MD, na? So starting point will be there first. MC minus MD is equal area of shear force in this portion, okay? This portion. So how will you calculate that? This is a rectangle, right? So ordinate is 40. This is our 40, right? This is our 2, right? That is our 40 into 2, 80. Value of MC is equal to minus 20, right? Minus MD, right? 80, okay? So value of MD will be 80 minus 80 plus, that is our 100, minus 100. So that is our minus 100. It will also be rectangle, right? This is rectangle now. Shear force diagram here is rectangle. So okay, bending moment diagram will be triangle, since the shear force is in rectangular diagram. So now we want to calculate the value of MA here, okay? So how will calculate it? So MD minus MA is equal area of shear force between D and A, okay? D and A. So MD, value of MD is already calculated, that is our 100 minus MA. Value of MA, we need to calculate that, right? So MD, D and A, what is the area available between D and A? So this much, right? So this much. So this is a trapezium, right? So how will you calculate the area of trapezium? You can calculate this or 80, this or 40. So you can calculate by two approach. You can just calculate this rectangle first, then you can sum this triangle area, or also you can also calculate half into these things are parallel, right? So B plus C into H. There is a formula, right? There is a formula of trapezium, right? So half into 80 plus 40 into this distance, right? This distance 2, okay? So 2 to cancel, there is our 80 plus 40, that is our 120. So we have only 120, okay? So 120, okay? So here 100 MA is equal 120 plus 100, okay? There is a minus. So MA is equal minus 220, okay? So here the load is triangle, right? Load shear force diagram is in triangle, so the bending moment diagram will be parabolic, okay? I think you understood everything. If you don't understand, you can just comment down below. Here one thing. So you can draw by this way. I just take some simple example. So you can solve the shear force diagram, shear force bending moment diagram for simply supported beam also. So okay, this is our shear force simply supported beam. Here it is our point A and B, okay? So here this is our C. So where the point load is acting vertically downward, that is our 20 Newton, okay? And here we have 20 Newton of UDL, okay, which is spread up to 2 meter. Here we have 2 meter, and here also we have 2 meter, okay? Now first of all, what we have to do? First of all, we have to calculate the reaction, right? So how do you calculate the reaction? So there is a basic approach to calculate the reaction. I will apply here. Okay, let us apply the basic approach. So first of all, vertical force RA plus RB, vertical upward RA plus RB is equal the downward force, that is a 20 plus 20 into 2, that is plus 20, right? So RA plus RB is equal that is our 20 into 40 plus 20, that is our 60. So that is calculating naming number 1. So now if I take moment, this is a hinge support, right? So in simply supported beam there is a hinge support. So if I take this hinge support, so the moment will be 0. If I take this point, so moment about B will be 0, right? So moment about B will be 0, okay? Okay, then we'll have, so this will give what moment? This will give clockwise moment, right? This will give clockwise moment and sagging moment, right? So if I consider this point, taking placing a thumb here, so placing thumb here, if I rotate the remaining hands, if I rotate the remaining hands, it will give clockwise moment, or it will give a sagging moment. So we know that sagging moment is positive. So that is our RA into how much distance? 2 plus 2 plus 2, that is our 6. So here this UDL will give negative moment. Why negative moment? Because it will give, if I place thumb here, then if you just rotate in the line of force of this 20 Newton, then it will give hogging moment, right? It will give hogging moment, na? It will be bending, right? It will be bending the moment. It will be bending the beam in this way, right? Here load is acting, na? So it will give this moment, right? So this is our hogging, right? Hogging is hogging means set beam, okay? This is our set beam, right? So this is our set beam. So this is our negative attitude. Negative attitude means negative, okay? So here negative 20 into how much distance? 2 distance. 20 into 2 distance, okay? Okay, this also vertically downward, so it will be negative because it will give anti-clockwise moment or sagging moment. So 20 into 2, okay? How much distance were there? 20 into 2 over the load, okay? How much distance? Vertical distance. So here 2 plus 2, that is your 4. 4 plus here central force is acting in the center, right? The force is acting in the center, right? So that is our 1. 2 plus 2 plus 2, 2 plus 2 plus 4 plus 1. That is our 5, okay? So minus vertical load 20 into 2, that is our 40. 20 into 2, that is our 40, equals 0, right? So calculating RA, you will get 40. So now we need to calculate the B, na? So if this is 40, then RB will be 20. Okay. Now we will calculate the shear force and bending moment diagram. This is 2 meter, here 2 meter, here 2 meter, okay? Now calculating shear force diagram here, I want to calculate from right to left, okay? I am here. At this instant, I have how many mangoes? Only RB mangoes. What is RB mangoes here? RB is 20, right? So 20 mangoes. So 20 mangoes will be positive or negative? That is right, upward, negative. I was going from right to left. That is right, upward, negative. This is upward force, negative. That will be minus 20 Newton. That is minus 20 mangoes I have at this instant, okay? Now at this point I have 20 mangoes only. If I do the diagram, then this is our vertical, right? This is our negative. Why negative? Because these were giving downward, okay? Not downward, upward. So this is upward, right? So right, upward, negative, okay? So this is our 20, okay? Minus 20. Up to this point we have 20. We had 20 up to this point. Now we had a suddenly vertical downward load. It will be positive, na? It will be positive. So 20 minus 20 plus 20, okay? So minus 20 plus 20. So minus 20 plus 20, I have zero shear force, right? So minus 20 plus 20, it will be 0, okay? Now at this point I am here. At this point, how many shear force, how many mangoes are with me? 0 mangoes, okay? At this point, how many mangoes are with me? 0 mangoes, okay? At this point I have 0 mangoes. At this point I have some mangoes. How many mangoes? 20 into 2, that is our 40. So here 0 mangoes. Up to this point 0 mangoes, but here in this point I have 40 mangoes. How will be the diagram? Diagram will be triangle, okay? Because the load diagram is UDL, so that is our 40, okay? So this will be the diagram. This will be positive, okay? So now I need to calculate the bending moment diagram. How will you calculate the bending moment diagram? So to calculate bending moment diagram, we know that there is a formula MA minus MB, not MA here, MB. MB minus MC is equal, this MC, no? This MC. Yeah, this MC. So MB minus MC equal shear force diagram between this shear force 20 into 2, right? This is 40, right? 40. one thing here, this is the shear force diagram is in negative, right? So we have to take the negative sign. Okay, mb minus mb is equal to 0 here. At this instant moment will be 0, right? So moment will be 0 here. MC, value of MC we need to calculate. So minus 40 here, minus 40. Okay, so the value of MC will be plus 40, right? Value of MC will be plus 40. So how will be the diagram? Diagram will be simply triangle, because since the shear force is in a rectangle, so I will have triangle, right? So triangle positive. Okay, these are 40. Okay, 40 kilonewton meter. Okay, at this instant there is no load, so we already discussed that if there is no load, then the shear bending moment diagram will be rectangle. Okay, so the bending moment diagram will be continued to this point rectangle. Okay, so now there is a shear force. Okay, there is a shear force, so it will be now at this instant how many bending moment available there? 40. No, this is still there will be 40 Newton. So here this is MD, right? So MD minus MA equal shear force diagram. So this is our shear force diagram. So this is our 40. This is 2. So half into 40 into 2, right? So here 2 to cancel. So we have 40. And here MD. So we need to find the MD value, right? Not MD, we need to find the MA value. So here available MD is minus or plus 40. Only 40 minus MA. So here MA is equal, we have here 40 and here plus 40 minus 40, right? So that is our value of MA is equal to 0. Okay, now value of MA will be 0, but here how will you connect this to this point? How will you connect that? In a rectangle, in a triangle, or in a parabolic way? It will be connected to parabolic way. How? Because here the shear force diagram is triangle, so the bending moment diagram will be parabolic. Okay, this is 0. So positive, everything is positive here. So in this way you can calculate shear force and bending moment diagram. Okay, you have to practice it again and again, then everything will be cleared. Okay, so this much is for today. So if you have any doubts, you can comment on below, and if you don't understand, and then I will try to make you understand in a new way. So okay, thank you.